Okay, we will start in 3 minutes. Okay, let's wait for 3 minutes, everyone. Okay, just to check, Ashley, can you hear me clearly? If you can, just reply me in the chat. Okay, checking again. Okay, Ashley or Arwen or Sharon. Okay, if you can hear me clearly, yeah, let me know. Okay, then I will actually start. All right. Okay, thank you, Ashley. Okay, so we still have 2 more minutes, but it's okay. We can start talking about this, okay, before we can start in 2 minutes, okay. Thank you, guys. Okay, so this is our first live stream, yeah, for the past year paper, yeah. So it's going to be, we are going to look into this paper for, okay, October, November 2021. Okay, it is a 2 hours paper, okay, so we will try to finish this, okay, maybe in 1 hour 30 minutes. Yeah, thank you, Sharon. Okay, so let's start. Okay, let's start on time. Okay, so here, okay, you have this paper. So the first question over here, okay, that we can see here is, when a dilute sulfuric acid is electrolyzed, water is split into hydrogen and oxygen. Now, this particular question, yeah, maybe if you just look at it from the surface, okay, it might look difficult, okay, but okay, if you follow, okay, whatever things that is mentioned over here according to the question, okay, you should not have any problem, okay. Like for example, now, okay, they say that calculate the number of hydrogen molecules produced during this electrolysis, and they have mentioned to you, okay, that you are using this cm cube of hydrogen, okay, so no need to worry about electrolysis. You can just know that, okay, like for example, 1 mole, okay, 1 mole, okay, contains 24 dm cube. Okay, and we know here, okay, you have 0.462 dm cube. You just need to convert. Okay, once you convert, you know that, okay, 1 dm cube is going to give you 1/24 moles. Okay, so if you are dealing with 0.462 dm cube, so what we need to do is going to be 1/24. You just need to times with 0.462, and you are going to be able to get the number of moles that is going to be involved. Okay, once you calculate the number of moles, okay, of the hydrogen molecules, you are going to find out the number of hydrogen molecules. You still need to times, because every 1 mole contains 6.02 times 10 to the power of 22 molecules. Okay, so you need to 23, sorry, you need to times with this number. Yeah, you need to times with this number. So here, once you find that, okay, you need to times with the Avogadro constant. Okay, once you times that, okay, I have calculated earlier. Okay, once you times, you are going to get this particular value, okay, 0.116 times 10 to the power of 23. Okay, and you can simplify, okay, which is going to be 1.16 times 10 to the power of 22. So I'm just going to write down over here 1.16 times 10 to the power of 22. That is going to be the number of molecules of hydrogen. Yeah. So if they ask you about number of atoms, then you need to times by 2. So this one is going to be number of molecules. Okay. Then, okay, they are asking you to calculate the total number of electrons transferred, okay, to produce this number of hydrogen molecules. Now, you do not need to worry about this entire equation over here, because the only thing that you need to worry is we are talking about hydrogen. So you just need to worry about this H plus, okay, you are going to add, okay, electron, and you are going to get H2, okay. So we are talking about 2 moles of electron, 2 moles of H plus, okay. So if you look over here from this equation itself, the half equation itself, okay, if you are talking about this certain number of moles, okay, this is going to be twice the number, okay. So we have calculated just now, if you calculate here the number of moles, okay, that number of moles here is going to be double. Okay, that's going to be double. So if you have calculated earlier, you can just use that value. Okay, but here, okay, you can relate to directly to the number of molecules. Okay, because I have calculated the number of moles, and then I have calculated with the Avogadro constant, and that is going to be which is going to be 1.16 times 10 to the power of 22. So this value, okay, should be double. Okay, if that is going to be your number of molecules, this value, the number of electrons, should be double than the number of molecules that you have. So that is going to be 2 times 1.16 times 10 to the power of 22. You just need to calculate that. Okay, if you calculate that, okay, you will be getting this answer, which is going to be 2.32. Okay, you take your calculator. Okay, you can check 2.32 times 10 to the power of 22. Okay, that is going to be a total number of electrons. Okay, now once you have this total number of electrons, that is going to give you that number of moles of hydrogen. Yeah, you are going to be asked to calculate the quantity of charge, okay, in columns, the total number of electrons calculated in B. Now, this is the number of electrons, okay, that you have calculated. If you look at your data booklet, okay, you will know that every 1 electron, okay, will have this particular charge, which is going to be negative 1.6 times 10 to the power of negative 19. That is going to be the charge of every 1 electron. So now you have 2.32 times 10 to the power of 22 electrons. You just need to times, okay? They want the quantity of charge, okay? They want quantity, not the negative value. So you can ignore the negative, but this one, they want you to times, okay? 2.32 times 10 to the power of 22. Yeah. So once you times, okay, you are going to get a value, okay, that is going to be 3.71 times 10 to the power of 3. And this one, you can leave it like this, or, okay, you can actually change it into 3710 column. Yeah, you do not need to give the value in negative because they want the quantity, yeah, the quantity of charge. So that is going to be 3710 columns. Okay. Now, after that, yeah, calculate the current X, okay, passed during this experiment. Yeah. So you know that, okay, we know that Q, okay, Q is the charge that we have, and then that is going to be equals to IT. You should know this formula. Yeah, the I, okay, is going to be given by X, okay, that is the one that we need to find, okay. The time, okay, the time they mentioned 14 minutes, okay, we are going to change this into seconds. So 14 times 60, okay, 14 times 60. And the Q, okay, we have calculated the Q, yeah, which is going to be 3710. So once you calculate, you just put it over there, 3710. You just need to look for the value of X, okay, X equals to 3710 divided by 14 times 60, which is going to be 840. If you calculate, you will get 4.42. Yeah, if you have your calculator now, okay, you can calculate, double check the answer. Okay, this is going to give you 4.42 ampere. Yeah, so this is how you calculate, okay, but you do not need to worry so much about the full equation. Okay, in the end, okay, we are just going to follow, yeah, the half equation, which is the 2H plus, okay, plus 2 electron to give me H2. Okay, just that. Yeah, so you do not need to worry so much about the full equation and worry about what's going to happen and so on. So you just need to follow the question, okay, from the top to bottom. Yeah, so all this we have calculated. Now the next is, okay, you have the standard entropies, okay, of the three species are given in the table. So they have given you this equation, and then they are asking you to calculate the entropy change. Yeah, the entropy change, okay, if you want to calculate, okay, it's supposed to be entropy, total entropy of the product minus the total entropy of the reactant. So you just need to calculate that. Yeah, so if you look at the total entropy of the product, okay, the product is going to be 2H2. So you need to times 2 times, okay, 131. So 131, you put a bracket, okay. Then the product also O2, okay, so 205, you put over there. That is going to be for your product. So you are going to minus the entropy of the reactant. Reactant is going to be H2O, 70 times 2. Yeah, so you do not forget with the number that you have in front. So 2 times, okay, 70. Okay, and you will get the entropy change. Okay, if you calculate, okay, you are going to get 262, okay, plus 205. Okay, you calculate, you minus 140. Okay, in total, you are going to get 327. Okay, and do remember the value 327 that you have is going to be a positive value. You need to indicate it's a positive value, and do remember it is in joule. Yeah, later when you do the calculation for the Gibbs free energy, we are going to look at that value, which is going to be, we are going to use kilojoule. You are going to change, so you need to be very, very careful with that. Yeah, so here they have given you this value. Okay, delta H, okay, is going to be positive 572, is an endothermic reaction, and they are asking you to calculate the Gibbs free energy. So do remember last time I told you Mr. Gopi is not so hot. Yeah, so Mr. Gopi is not so hot, it's going to be delta H, okay, not so this one, okay, not so hot. Yeah, so you just put over there, okay, and you just need to calculate. Delta H is going to be 572, yeah, kilojoule. Yeah, you just need to be careful with that. Temperature is 298 Kelvin. Yeah, and then entropy change you have calculated, but you need to be very careful. It's not 327 only. You need to divide by 1000. Why? Because it was in joule. You need to change it into kilojoule. This is the common mistake that all the students will make. Yeah, so please be very careful with this. Okay, if you calculate, okay, you are going to get 572 minus 97.446. Okay, if you have calculator with you, calculate. Okay, you are going to get 474.554. Okay, kilojoule per mole. Okay, and I'm going to use, okay, 3 significant figures over here. So I'm going to just write down as 475. Okay, 475, and do not forget this, okay, because it's a positive value. Okay, for chemical energetics, please make sure, yeah, you put the symbol over there, which is going to be positive 475 kilojoule per mole. Now, the next part is predicting the effect of increasing temperature on the spontaneity of this reaction. Now, this reaction, okay, we have learned that, okay, if you have delta H, okay, the delta H is endothermic, is positive, okay, and we also know that, okay, your entropy change is going to be a positive value also. Yeah, last time, okay, I told you that whenever we have, okay, the same symbols for the enthalpy change and entropy, okay, we need to look at the temperature to find out, okay, under what condition this reaction is going to be spontaneous. This will apply for enthalpy, which is negative, and entropy, which is going to be negative as well. Yeah. So how to do this in an easy way is going to be, you just need to put ice, okay, you just need to put water over here, okay, and we know the change from ice to water is going to be endothermic, so delta H is positive. And we know from ice to become water, ice is going to be solid, water is liquid. So the entropy change is also going to be positive. So it's a good representation, yeah, for this condition. And under what condition ice tends to spontaneously change into water? Of course, after 0 degrees Celsius, which is going to be at higher temperature. This is going to help us, okay, to identify that this reaction is going to be spontaneous when, okay, the temperature is higher. This is going to be something that is going to help you to predict. So in this case, when I predict the effect of increasing temperature, the reaction, okay, is going to be more spontaneous. Okay, so you need to explain. Okay, so this one is going to be spontaneous. Okay, spontaneous. But you need to explain why. Okay, in order to explain why, you need to look at the Gibbs free energy. Mr. Gopi is not so hot. Yeah, so delta H. Okay, this one. So what happens over here is, okay, the only variable that we are changing over here is the T. And we know if the T is going up, okay, what happens? This entire value is changing. It is going to go up. Okay, so what will happen? Okay, what will happen? Okay, your Ts, okay, your temperature times the entropy change, okay, they are going to become, okay, as they go up, they are going to become greater than delta H. Okay, if that value is greater than delta H, because it's going to be minus, okay, you're going to deduct. So what will happen to your Gibbs free energy? Your Gibbs free energy will start to go less than 0. Yeah, and Gibbs free energy, if it is negative, okay, then it's spontaneous. So how do I explain this? Okay, you just need to tell when temperature increases, okay, your T, this value, okay, increases, okay, until this T value, okay, becomes greater than delta H, okay, making the Gibbs free energy to become less than 0. Okay, you explain, okay, accordingly. And when Gibbs free energy becomes less than 0, which is a negative value, then the reaction is going to be spontaneous. Okay, so this is how you explain to get this 1 mark. Okay, do remember you need to explain. Yeah, if you don't explain, you are not going to get the mark. Yeah, so this is going to be predicting the effect of increasing temperature. So that's going to be a total of 9 marks for this particular question. Okay, let's move on. Okay, so when we look at question number 2, okay, solution Y, okay, is going to be hydrochloric acid, and this is going to be a strong acid. Okay, so you have a strong acid and you have solution Z, which is going to be 4-chlorobutanoic acid. So it's going to be something like carboxylic acid now. So they have mentioned, okay, this carboxylic acid definitely going to be weak acid. So weak acid, they will definitely have the Ka value. So in this case, they are giving you the pKa value. Yeah. And they have mentioned the pH of both solution is 4. Now, the common mistake or the common assumptions of students is going to be they think that, oh, these two mixture, okay, when they go and add, then only it's going to be 4. They never say that this solution Y and the solution Z is going to be added or mixed. Read the question properly. So it means that individually, solution Y, pH is 4. Individually, solution Z, pH is going to be 4. So this one, you need to be careful. Now, write an expression for the Ka value. Yeah. So this one, okay, if I write down Cl, okay, you have CH2, 3, CO2H, okay, they are going to partially dissociate to give you Cl. You just need to repeat this. CO2 minus plus H plus. Okay, just this one. And when I write down the Ka value, the expression, the expression of Ka, it's going to be product divided by reactant. Don't shift the places. So here, okay, we look at the number of the one in front of us. Okay, all this is going to be 1, so nothing to do with to the power of something. No need to worry about that. You just need to put a bracket to show the concentration of H plus, okay, and then the Cl, CH2 3 times CO2 minus, put a bracket, okay, because these are the products, and then you divide by the reactant, which is going to be Cl, CH2 3, CO2H. Make sure you close the bracket. This is the expression for Ka. Now, write a mathematical expression to describe the relationship between Ka and pKa. So the relationship between this, quite simple. Okay, if you want to write down pKa, then negative log Ka. You can answer like this. Okay, or okay, if you want to use Ka, okay, Ka, if you are good in maths, this is going to be 10 to the power of something. So if you bring over there, so 10 K to the power of negative, you bring up negative pKa. Okay, if you write down like that, also can. Okay, so choose one. Okay, choose one. Don't give both. So you can actually give any of these two. And then calculate the H plus in solution Y and Z. This is the part that students will get confused. Remember just now, I told you for both, okay, pH is going to be 4. So it doesn't matter. Okay, you can just use the common equation, which is going to be, if you have pH equals to 4, okay, we can calculate what is going to be the concentration of H plus. Quite simple, because pH equals to negative log concentration H plus. Okay, so if you want to find out what is the concentration of H plus, okay, it's going to be quite simple. Concentration of H plus is going to be 10 to the power of negative. You bring over there, then pH you put over there. So it's going to be 10 to the power of, okay, pH is 4, negative 4. Okay, and this one, okay, you can just simplify and just say 1 times 10 negative 4, okay, mole per dm cube. So that is going to be my concentration of H plus, not only in one, okay, in both Y and Z. So 1 times 10 to the power of negative 4. That is the concentration. And then finally, they are asking you to calculate the ratio. So sometimes students get confused. What is this and what is this? Okay, you need to do it separately. So here they are asking the concentration of HCl. The concentration of HCl. And we know, okay, HCl dissolves or dissociates or ionizes completely. So to give you H plus and Cl minus, if you have concentration of H plus as 1 times 10 to the power of negative 4, okay, you are going to have the same concentration over here, because 1 mole to 1 mole. So this one, no need to worry, you have already found out. Okay, 1 times 10 to the power of negative 4. Okay, so the next thing that we need to find out is going to be for this. This is going to be the weak acid. The weak acid. Now for the weak acid, okay, we have the formula. Okay, what is the formula? Okay, the formula is, you already know the H plus. Okay, using H plus, how do you find out the concentration of a weak acid? Okay, the formula is going to be, if you have Ka, okay, if you have Ka, the formula is concentration of H plus to the power of 2. Okay, and why we have all these formulas? I think you can refer to my lectures, yeah? So how we can derive to get this formula. So you are going to be divided with HA, which is going to be this, yeah? The weak acid, okay? This is going to be the formula. And we know, okay? Do we know what is the Ka? Okay, the value, okay, the pKa is given 4.52, yeah? So we can calculate using pKa value, you can calculate what is going to be the Ka value, okay, which is going to be the pKa is going to be negative log Ka. So if you have 4.52, okay, you want to find out what is Ka. Okay, Ka equals to 10 to the power of negative 4.52. Okay, if you calculate, that, okay, you are going to get, okay, the value is going to be, okay, 3.02 times 10 to the power of negative 5. Okay, so I'll just put 3.02 times 10 to the power of negative 5. Okay, using this value, okay, you just need to calculate, okay, the HA, because we already have this value. Okay, just need to put it in. So it's going to be 1 times 10 negative 4. Just now we have calculated, to the power of 2, okay, equals to 3.02 times 10 negative 5 divided by concentration of HA. So you can calculate what is the concentration of HA, the weak acid. So it's going to be 1 times 10 negative 4 to the power of 2 divided by 3.02 times 10 negative 5. If you calculate this, okay, you are going to get, okay, the value is going to be, okay, 3.31 times 10 negative 4. Okay, 3.31, okay, times 10 negative 4. Okay, once you get that value, okay, you just need to solve this question. They want the ratio, okay, they want the ratio. So HCl, okay, we know, okay, the ratio is going to be HCl, we have calculated 1 times 10 negative 4, okay, divided by this value 3.31 times 10 negative 4. Cancel. So it's 1 over 3.31. Okay, if you calculate, okay, you are going to get 0.302. Okay, 3 significant figures. So you just need to put 0.302 there. Okay, that's going to give you the 2 marks. Okay, so the next question, okay, a buffer solution of pH 5. So this is a buffer solution, acidic buffer solution. You are going to produce by adding sodium propanoate. So this is going to be the salt, okay, to a weak acid, which is going to be 5 grams of propanoic acid in 100 cm cube of distilled water. And you are going to calculate the mass of sodium propanoate that must be used, okay, to achieve this pH. And Ka is given. So all the other things are given, okay, but how to start? I think this one is related to pH of buffer. Okay, you need to know the formula. Okay, so you just need to memorize only. No need to worry so much. Okay, but if you don't want to memorize, you want to derive also can. You should be able. Okay, if you understand the concept, then you should be able to derive. Okay, so pH, okay, is going to be pKa, okay, plus log, okay, salt divided by acid. So this is going to be the formula that we are going to use, okay, for this acid buffer. Okay, so the pH is going to be 5. I just put 5. Okay, the Ka value is, okay, 1.35 times 10 to the power of negative 5. I just need to find out what is the pKa value. pKa value is negative log 1.35 times 10 negative 5. If you do that, okay, the pKa value is going to be 4.87. So I'll just use the value 4.87 directly over here. Okay, now plus, okay, log, okay, concentration of the salt, okay, here, okay, the salt, you see the salt that we are going to use, okay, we need to find the mass. So to find the concentration of the salt, I just put mass, okay, divide by, okay, it means now I need to find out the mole, yeah, mass divided by the salt is 96. I just put 96 over here. And then, okay, that is number of moles only, okay. The volume, okay, is going to be 100 cm cube. So I just use 0.1 dm cube. So I just put divide by 0.1. That is going to be my concentration of my salt. And then divided by, okay, do remember just to create clarity over here, I just put log over here. Then, okay, divided by 5 grams, the acid, yeah, 5 divided by 74. This is still number of moles, yeah. Then divide by 0.1, which is going to be your volume. And from here, you can cancel, you can simplify. This one and this one, no need. Okay, you can simplify. And you can also simplify, okay, which is going to be 5 equals to 4.87 plus, okay, log, okay, then here, m over 96 times, okay, 74 over 5. Okay, you can just put it like this, okay, and okay, you simplify all this, okay, you try to find out what is the m value, okay, you just you will have, okay, this one is 1.35, you will get 1.35 equals to 74 m over 480. You can just try to solve this, okay, you will come into this. And then, okay, if you want to find the m, you will be able to end up to get this 8.75 gram. So I will actually put 8.75 gram over here. Okay, that is going to be the mass of sodium propanoate. Yeah. So let's actually move on. Okay, so that is going to be 3 marks. Okay, some of this, some dilute sulfuric acid is mixed with small sample of this buffer solution. Do remember this buffer solution pH was 5. Yeah, so you are going to add the sulfuric acid. Okay, and then the final pH of the mixture, suddenly you get pH which is going to be 1. If let's say the buffer is working, yeah, the buffer will still maintain the pH at 5. Okay, but if you have the pH of the mixture close to 1, it means the buffer, yeah, this one you have already exceeded the buffer capacity. Yeah, so in this case, what happens over here? So we know, okay, whenever you have, okay, any buffer, in this case this buffer, okay, you have the salt, okay, they are going to give you this equation. Okay, if you have the salt, okay, so you have 2 equations, okay, which is going to be 1, okay, the first equation. And then you have the second equation, which is going to be a reversible reaction, which is for the acid, and that the carboxylic acid. And if I have H plus, normally what happens, the H plus is being removed, okay, by shifting the position of the second equation to go to the left. Yeah? So in that sense, you can remove the H plus, okay, and then in that process also, yeah, the salt over here, okay, it's going to actually decrease, okay, but the decrease is compensated, okay, by this high reserve, okay, from the salt. Yeah, so in this case, okay, if you have a lot of H plus in this particular case, when you add the some dilute sulfuric acid over here, what happens? Okay, the H plus is too much. Okay, until, okay, it has already reacted with all the propanoate ion. Okay, they have reacted with all the propanoate ion until there is not enough propanoate ion, okay, to remove the H plus. So the H plus will stay. The H plus from the acid will stay over here. So they, you can say the total propanoate ion is not enough, okay, to react with all the H plus that is being added over here. So if you want to get the 2 marks over here, what you need to mention, okay, you can say that, okay, the CH3, CH2, COO minus ion, okay, has, okay, completely reacted with the H plus. Okay, the additional H plus, okay, could not be changed, okay, to CH3, CH2, COOH by the buffer system. Therefore, okay, the pH cannot be maintained at 5. Okay, so it actually goes to 1. Okay, so that is going to give you the 1 mark. Okay, completely reacted. There is no more, okay, or not enough, okay, propanoid ions. Yeah, so you do not have enough propanoid ions to shift, okay, the position of the equilibrium to the left. Okay, no more. Okay, so they cannot move to the left anymore. Yeah, so in this case, okay, this is going to be the 2 marks. And now, okay, 10 marks done. Yeah. So the next part, okay, is going to be, okay, question number 3. Now, this question asks you to define the term electron affinity. Now, what is electron affinity? Okay, electron affinity is going to be the enthalpy change. You need to be, normally if you find it from the textbook, they are very specific. They say first electron affinity, second electron affinity, and so on. But this one is going to be general. So you just need to give it general as well. Enthalpy change, okay, when 1 mole of electrons, okay, 1 mole of electrons, okay, is added to 1 mole of this is important, gases, okay, gases atom, okay, or, okay, ion. These are general. Yeah, so it can be also be affected, be applied for let's say second electron affinity, third electron affinity, or what. Yeah, gases atom of ion, okay, to form, okay, to form 1 mole of gases. No need to say -1. Okay, gases negative ions. Okay, under standard condition. So important. Okay, it's going to be 1 mole of electron is being added. Okay, and then, okay, you are going to add to 1 mole of gases atom or ion to form 1 mole of gases negative ions. Yeah, so it must be gases as well. Okay, that will give you the 2 marks. Okay, do remember definition involving 2 marks. They are very, very strict. Yeah, you need to have, okay, the certain things that they are looking for, which is going to be the 1 mole of electron being added, 1 mole, okay, gases, yeah, to form 1 mole of gases negative ions. Okay, now write an equation. So this one is apart from electron affinity. They ask you write an equation for the process corresponding to the second ionization energy of calcium. Include, okay, the state symbols. Okay, so if you include the state symbol over here, second ionization energy of calcium. So calcium, it means the first, you already remove it. So it's going to be calcium, Ca plus, and you are removing another electron, so Ca2 plus, gas, and then you have electrons. So this is going to be the second ionization energy of calcium. Make sure the gaseous state is shown. Yeah, if you don't show, you are not going to get the mark. Okay, now the next question is going to be some of the data relating to calcium and oxygen are listed. Okay, select relevant data from this list for your answers in C, D, and E. So here, okay, they say oxygen always exists in O2. Okay, and use the data to calculate the value of the bond energy of O double bond O. Yeah, so it means if you break the O double bond O, okay, you are going to get 2 atoms of oxygen. Okay, so we just need to find out what is going to be that energy, yeah, for the bond energy for that. Okay, but they didn't give you directly. Okay, you need to find out using the data that you have over here. Now, if I look at the data, let's actually look at the data. I can see, okay, this is slightly different than the data that I normally get. Okay, for my drawing for Born-Haber cycle. Yeah, why? Because you don't normally see something like this. Yeah, so maybe later we can look into that. But okay, the one that is important for C, okay, is going to be this data, okay, because this data is telling you half O2, okay, which is in gas, okay, plus 2 electron is going to give you O2 minus gas. Okay, this is going to tell us, okay, something to do with electron affinity. Yeah, but they do it like they combine. Yeah, they combine. They didn't do it one by one. First electron affinity, second electron affinity. So it definitely got to do with electron affinity, which is these two. Okay, so what I can see is I can combine. Okay, I can combine this equation, because if I use these two equations, okay, I will get the O in form of negative ion, and I can somehow, okay, use this value, okay, to calculate my bond energy value. I'll show you. Yeah, the first electron affinity, if you look at this data over here, first electron affinity, we know that oxygen, okay, they are going to add electrons. So oxygen add electron, they are going to give you oxygen minus. And we know, according to our definition, okay, 1 mole of electron is added to 1 mole of gases atom or ion. So this one must be gas. Okay, this one must be gas. Okay, so I just put over that. And if it is going to be the second electron affinity, okay, so it means it's already O minus gas. Okay, you add another electron, you are going to get O2 minus gas. Okay, what I can do now, okay, I can combine these two equations, okay, where, okay, if I combine this, okay, I will notice that, okay, there are certain values will disappear. Like for example, this one and this one, they are the same. I can cancel. Okay, when I combine, I will get O gas, okay, plus 2 electron to give me O2 minus and gas. And if I combine, it's going to be 844. Okay, plus with negative 142. Okay, if you calculate that, okay, if let's say we quickly calculate 844, 142. Okay, 20702. Yeah, so you will get positive 702. Okay, so I'm going to use this value, okay, or this equation to find, okay, my bond energy. Yeah, so if you look over here, okay, if I rewrite this, okay, oxygen, okay, oxygen, okay, before I just straight away rewrite, okay, I can see here I have the O2 minus. Okay, here I don't have O2 minus. If I want to calculate, okay, I have O2 minus over here. Is there a way where I can eliminate the O2 minus? There is a way. How? You put the O2 minus here, change the equation, okay, O2 minus gas to give me O gas, okay, plus 2 electrons. So you are changing the position of the equation. And if you change the position of the equation, positive 702 will become negative 702. Okay, and I am going to put it over here, okay, O2 minus gas, and then they are going to give me O, which is gas, okay, plus 2 electron, okay, which is going to be I put negative 702. Okay, and let me bring this up. Okay, put them up. Okay, and we know that this particular value, okay, the one that we took just now is going to be positive 951. Okay, I can join these two equations. Okay, when I join these two equations, I will notice that I am able to cancel this and cancel this. Left and right will cancel. I will be able to cancel this and cancel this as well. Left and right, it will cancel. So I will have half O2 gas, and it is going to give me O gas. Okay, and this value is 951 plus negative 702, okay, which is going to be, if you calculate, you will get 249. Okay, a positive 249. Yeah, 249. Okay, so you get this value. Now, this is, okay, if you want to find the bond energy is going to be O2 gas to give you 2O gas. Okay, and I know that this value is 249. Okay, so if you want to find the bond energy, the OO double bond, yeah, so you just need to change this equation to this equation. What you need to do, you times by 2. Okay, you times by 2, you will get O2 gas. Okay, and then you get 2O gas. Okay, so this one you times by 2 is 249 times by 2. You get positive 498. And this positive 498 is actually going to be the bond that is broken, okay, between oxygen and oxygen, which is going to be the bond energy that we are looking for. So that is going to be what we are looking for just now. Yeah, positive 498 kilojoule per mole. Yeah. Now, so let's move on. Okay, so make sure it's positive. You put the positive over there. Okay, that is the bond energy. Now, suggest why, okay, the first electron affinity of oxygen is negative. What is electron affinity? Electron affinity, when you get 1 mole of electron, you try to bring in, okay, to the atom. Yeah, normally when you bring in to the atom, yeah, we are talking about, if it is negative, it means we are talking about some sort of bond formation. So we can say, okay, because there is we are trying to form, yeah, bonds between the electron and the ion. Yeah, so we say that the electron neutral, so which is going to be the proton. Okay, because negative, okay, negative charge from the electron, okay, and the positive proton, yeah, from the nucleus, opposite charges they attract. Okay, so you can say because there is an attraction, okay, between the negative charge, okay, the negative charge is coming from the electron, okay, that we are going to bring in, and, okay, the positive charge, okay, from the nucleus. Okay, so you are going to have attraction. Okay, so it means some sort of bond formation. Therefore, okay, your the enthalpy, okay, the enthalpy is going to be negative. Okay, because it's similar to bond formation. Okay, now suggest why the second electron affinity of oxygen is positive. Now, when you add the electron to the oxygen, you are going to get O minus, okay, O minus. And if you have the electron, which is a negative charge now, okay, you can see this is negative charge, this is negative charge. You are going to have negative and negative. They are going to repel. Yeah, but you still want to bring the electron over there, so you need to provide energy. Yeah, you need to overcome the forces of repulsion. Okay, therefore, okay, the enthalpy is going to be positive to overcome. Okay, to overcome the repulsion. Okay, from what? The repulsion between, okay, opposite, between the same, okay, the same charges, okay, of electron and the negative ion. Okay, that is going to be why it is going to be positive. You need to overcome. Okay, so it's like something like you try to force them. So you need, in order to force them, you need to be like the energy is going to be absorbed. So it's going to be endothermic. So that's why it's positive. Yeah. Now, the next part is going to be calculating the enthalpy of formation, okay, of calcium oxide. Yeah. So if you want to form calcium oxide, okay, so we normally draw the Born-Haber cycle. Okay, but for this equation, okay, the Born-Haber cycle, okay, they involve some sort of shortcuts. Okay, why? Because, okay, the shortcut, okay, will involve, because we are talking about all this information over here. Like, for example, okay, we normally, okay, we atomize calcium. Okay, then, okay, we are going to ionize calcium, but they have already done that. They have already changed calcium solid to become gas. They have changed the calcium gas to become Ca+, and they have changed up to Ca2 plus. Okay, so it means they have bypassed certain reactions. Okay, so it means that from the Ca, which is going to be solid, I'm trying to react with O2, which is going to be gas. Okay, and this one is half, which is going to give me CaO. Yeah, so here they have bypassed certain equations. Okay, so they are going to reach this part, which is going to be calcium 2 plus gas. Okay, and then you have 2 electrons. They have removed. Yeah, they already ionized. Okay, they already atomized, they already ionized. Okay, and then you get that. Okay, do remember they didn't do anything yet to the oxygen, so I just put half O2 like normal. Yeah, now that value is going to be plus 1933. Okay, that value is going to be plus 1933. So now, we know that, we have calculated the gas, the half O2, you can change them into, you can atomize them. Okay, you can atomize them. Then after that, you can also do electron affinity, yeah, and so on. Okay, but what they have done, they have even bypassed that step. Yeah, they have bypassed the step, which is going to be if you put the O2 here. If you look over here, I have actually included. Yeah, so what I did was, I atomize the oxygen. Yeah, atomize the oxygen, which is I'm going to use the 249, the value that I have calculated just now. Yeah, the value just now is O2 to become 2O. Yeah, that's 249. Okay, but sorry, that was not 249. That's 498. Yeah, so I need to divide by 2. Okay, which is I'm dealing with half O2 to become O. So I need 249. Yeah, so I use the 249, and after that, I need to still bring in 1 electron and another electron. Yeah, 2 electrons came in. So I use the first electron affinity and second electron affinity. I add them. Okay, I add these 2. I get 702. I put it over there. Actually, you do not need to do that because from here all the way to here, they have given you the value, which is going to be 702 plus 249, is going to be this value. They have already given this. 746 plus 249 is 952. Yeah, so you can actually bypass that value. So I will just use the 951. Yeah, so from here to here, I'll just straight away put Ca2 plus, and then you are going to get half O2 plus 2 electron to give you O2 minus. So it means that O2 minus, this is gas, this is gas. That value is 951. I have this 951, and then I am going to react. Now I'm going to actually have the lattice energy. Lattice energy is going to be from the gaseous ion. Then you are going to form the solid, the calcium oxide solid. That value is given negative 3517. Negative 3517. So if I select this and I bring it down, let me put it over here. If I put it over here, we know that if you go and add up this value and this value, if you add up, you are going to get, you can calculate 951 plus 1933, 1933, 951, so you get 2884. okay, the left hand side is 2884. The right hand side, okay, which is here, negative 3517, which is longer, yeah, which is going to be longer. So this is going to tell us that your enthalpy of formation, yeah, this is the enthalpy of formation, is negative, I can say. Because why? Okay, these two, when you add, must give you the 3517 lattice energy, yeah. So I know that this value must be negative, okay, must be negative. So how to solve that? Okay, you can see 3517 and then 2884. What is the difference over here? Okay, if you know maths, I think straight away you can just write down, okay, 3517. Okay, then you minus, okay, with 2884. Okay, once you minus that, you are going to get 633. Okay, once you get 633 over there, okay, you just need to apply them over here, which is a negative value. It's going down, yeah. So it's going to be negative 633. Yeah, that is going to be your enthalpy of formation, yeah, for the calcium oxide, yeah. So that is the value, and this is how you draw, okay, the Born-Haber cycle. They didn't ask you to draw, okay. You should be able to produce this and should be able to make sense of this, yes. That's why I show you, yeah. The lattice energy, the next question, the lattice energy of lithium fluoride is given negative 1022, yeah. And then they ask you the factor, identify the factor that causes the lattice energy of calcium oxide, okay, lithium fluoride Li plus, F minus, calcium oxide, okay, calcium Ca2 plus, O2 minus, okay, to be more exothermic, okay, than lithium fluoride. Okay, this one, okay, lattice energy, okay, depends on charge density. So if you look at this ionic radius, okay, and then the charges, okay, charge density, okay, it depends on the charge divided by radius, okay. So in this case, the one that is more obvious over here, okay, is going to be the charge, okay, because positive 1, negative 1, positive 2, negative 2, okay, the charges is more. So if you want to identify a single factor over here, you can say the charge, okay, the charge, okay, for the Ca, okay, 2 plus, okay, and O2 minus, okay, is more, okay, than LIF, okay. Therefore, okay, if the charges are more, okay, it means that the positive and negative, they are going to be attracted more. Lattice energy means what? We are going to bring the gases, gases ions, we are going to bring them together to form the solid. So it means that they are going to be attracted more, okay? So more charges, okay, they are positive and negative, they are going to be attracted. But if you have positive 2 and negative 2, they are going to be attracted more, okay? So therefore, the attraction, okay, is greater, okay? The attraction between oppositely charged, okay, oppositely charged ions are greater, okay. So therefore, okay, the lattice energy is going to be more exothermic, okay. Because why? Okay, lattice energy is more exothermic, okay, because it's going to be bond forming, okay. Therefore, it's going to be exothermic, of course, okay. So that is going to give you the 2 marks, okay, for this question. Okay, let's move on. Okay, for question number 4, separate samples of, okay, 0.2 moles of calcium carbonate and 0.2 moles of barium carbonate are heated, okay, until completely decomposed to the metal oxide and carbon dioxide. So if I have calcium carbonate, okay, so you heat, you get calcium oxide plus carbon dioxide. If I have barium carbonate, okay, then I heat, I will get barium oxide and carbon dioxide. So you do that, yeah, you will decompose. So they say that which of these 2 group 2 carbonates require higher temperature before it begins to decompose. Now, this one we have learned in AS, okay, but the explanation we have learned in A2, yeah. The barium carbonate, okay, is going to be more, they are thermally stable, okay, thermally stable. and we learn only about it is thermally stable going down. Group 2 carbonates going down the group, they become more thermally stable. But in A2, we have learned why. When we talk about stability, we talk about the polarization, the ion polarization. So if you look at calcium is small ion, compared to barium, which is lower. Barium ion is going to be a larger ion. If I want to represent this, the barium ion Ba2 plus and Ca2 plus, barium 2 plus is a larger ion. If it is a larger ion, they are not able to polarize the carbonate. The carbonate ion, they are not going to be able to polarize this. So it means that the electron cloud, in carbonate ion, they are not distorted. So if they are not distorted, the bond between carbon and oxygen are less weakened. So they are less polarized, and the bond is less weakened, compared to calcium. Calcium is smaller, they will polarize more. So that is going to be the explanation. So if I enlarge this, you can see which one of them, which one is going to be require higher temperature before it begins to decompose. Of course, because it's difficult to decompose, it's going to be barium carbonate, so it requires more temperature. So barium carbonate. Why? Because barium carbonate is more thermally stable, because the barium ion is larger, you can say the ionic radius is going to be more, and they do not polarize, or they polarize less, the carbonate ions, or the carbonate ions are less polarized. The carbon oxygen bonds, they are not distorted, and less weakened. They are less weakened, and requires more heat to be broken. So if you have calcium, yes, they will actually distort more, and then the bond is going to be weakened. In this case, less weakened, you require more energy to be broken. Let's move on. Now, after the decomposition is complete, so after they change into barium oxide, calcium oxide, you take the sample, you put 2 dm cube of water, a solution is formed, no solid present, so it means they dissolve everything. So you take the calcium oxide, then they put water, you should get calcium oxide. You add water, you are going to get calcium hydroxide. Dilute sulfuric acid is then added dropwise until a precipitate is seen. So if you have H2SO4, we are talking about, you are going to see calcium sulfate. So the precipitate that they are talking about, is most likely calcium sulfate. Now the same procedure is repeated with barium oxide. So barium oxide, you will get barium hydroxide, and then you add drop by drop H2SO4, and you are going to get barium sulfate. So barium sulfate is going to be, everyone should know, it's white precipitate. So here, if you look at the sample, they say identify the sample to which most sulfuric acid must be added to cause precipitate to appear. It means that they are talking about the hydroxide. Which one, difficult to they're talking about the solubility of hydroxide. So if you look at the solubility of hydroxide, for both sulfate and hydroxide, as you go down the group, sulfate and hydroxide, as you go down the group, the hydroxide, so I think if you look at sulfate, it's going to be slightly different. So hydroxide, for hydroxide, the solubility is going to increase. Solubility increases going down. Solubility increases. Group 2 solubility. Sulfate, on the other hand, as you go down, we know this is a white precipitate. So everyone should know, as you go down, solubility decreases. okay, because this is a white precipitate. Okay, so here, okay, they say that which sample, okay, means for the hydroxide. Yeah, let's talk about hydroxide. Which sample, okay, you must add more sulfuric acid. Yeah, so the sample that you need to add, okay, because the solubility increases, this is more soluble. Okay, so the one that you need to add more, okay, is going to be the calcium hydroxide. Okay, so for calcium hydroxide, okay, you need to add, okay, more, okay, add more H2SO4, okay, because, okay, it is less soluble. Okay, less soluble. So you add more, yeah, and then explain your answer. So the answer, okay, here, okay, when you explain, okay, you should refer. So one of the explanation is going to be it is going to be less soluble. And then you need to also refer to the solubility of the precipitate. Now they're asking you to talk about solubility of the precipitate. Now, precipitate is calcium sulfate and barium sulfate. Yeah. So if you talk about the precipitate, okay, so if barium sulfate, okay, barium sulfate is less soluble. Okay, it's less soluble. And if you want to talk about barium sulfate being less soluble, okay, than calcium sulfate, you need to refer to your lattice energy, enthalpy of solution, and enthalpy of hydration. Okay, this one, okay, we have learned, okay, last time. Okay, if you are talking about, okay, your enthalpy of if you're talking about sulfates, okay, if you're talking about sulfates, okay, you need to talk about, okay, hold on, okay, you need to talk about, okay, you refer to what I taught you last time, okay, about the group 2 sulfates and group 2 hydroxide. If sulfates, okay, let's talk about sulfate. If sulfates, then you need to talk about the lattice energy. Both of them, the size is increasing, but the lattice energy, okay, lattice energy, they will decrease smaller volume. They will decrease, but smaller volume. Okay, but the decrease of hydration, okay, enthalpy of hydration is going to decrease more, okay, bigger value compared to lattice energy. Okay, this is for sulfate. Now, if this happens, okay, we know that, okay, the formula, okay, is going to be lattice energy plus enthalpy of solution is going to be enthalpy of hydration. Okay, we know this. Okay, and if let's say, okay, if you want to refer to enthalpy of solution for solubility, yeah, it's going to be a hydration. Okay, hydration minus the lattice energy. And we know that hydration is decreasing more. If hydration is decreasing more, okay, what can you say? Okay, you can say that your enthalpy of solution, okay, is going to become more positive or endothermic. Okay, so if your enthalpy of solution is endothermic or positive, okay, we know that in order to say something is soluble, okay, your enthalpy of solution must be negative or a small positive. But in this case, okay, because your hydration is decreasing more than the lattice energy, okay, your enthalpy of solution is getting positive. Therefore, okay, the solubility, okay, is going to decrease. The solubility of what? Solubility of barium sulfate. Yeah. But if you want to change, okay, in terms of hydroxide, because they say precipitate, but if you want to change about hydroxide, then you just need to change. Yeah. Change in what? Okay, here I say smaller and hydration is bigger. You just need to change. Decrease in lattice energy is greater than decrease in enthalpy of hydration. So this one, please take note. Okay, so this one, please go through. If you don't understand, please go through. Yeah, so when you explain, you get 3 marks for this. Okay, next part. okay, calculate the mass in gram, okay, carbon dioxide produced, okay, by decomposition of 0.02 moles of calcium carbonate. So calcium carbonate is going to give you calcium oxide plus carbon dioxide. So if you have 0.02 moles of calcium carbonate, 0.02 moles of this, and we are going to look for calcium, carbon dioxide, of course, you are going to get 0.02 moles of carbon dioxide also. Okay, but they want in mass. Okay, so we know number of moles is going to be mass over mR. Okay, carbon dioxide is 12 plus 32 is 44. Okay, so you can calculate what is the mass. Mass is going to be 0.02, the number of moles, times 44. Okay, if you times by 44, you will get 0.88 gram. Okay, a simple calculation. Yeah, and then calculate, okay, the minimum mass in gram of propane that would, on complete combustion, produce the same mass of carbon dioxide calculated in C1. This is very simple. Propane C3H, this one propane, so CnH2n plus 2, yeah? So double 6 plus 2, 8, yeah? So plus O2, you just need to balance the equation. You will get carbon dioxide and water, so you just need to put 3 over here. You balance, you just put the 4 to get the 8. Oxygen, you count 4 oxygen, 6 oxygen, total 10 oxygen. So you just put 5 over there. Okay, once you put the 5 over there, so you have everything balanced over there. And then now you just need to solve this. Okay, so how do you solve? Okay, you just need to put, okay, the values. Okay, so just now, okay, we know that 0.02 moles. Okay, so if I have 0.02 moles over here, so of course this one is going to be divided by 3. So how many moles? 0.02 divided by 3. Okay, refer to the moles, don't use the mass. Yeah, so once you have that, you can just convert to mass, okay, which is going to be number of moles equals to mass over mR. Okay, so number of moles is this one. Okay, so I just want the mass. So mass is number of moles times 0.02 divided by 3 times with mR. mR is going to be, okay, C3H8. So 3 times 12, okay, plus 8 times 1. Okay, so it's going to be 36 plus 8. You will get 44. Okay, so you need to times by 44. If you calculate, you get 0.293, okay, gram. So you just need to put 0.293 gram. Done. Yeah, so quite simple. I think the one that they give you, this one C, is quite simple. I think the one that is difficult is more towards this part. Okay, all this part, okay, maybe taking more time. Yeah, but if you move on, okay, let's go to question number 5. Okay, so MnCl4 is a complex ion. Deduce the oxidation state of manganese in MnCl4. Yeah, this is quite simple. So you just put X, okay, plus, okay, 4 times -1. Cl is -1. Equals to -2, so X is -4, -2, X is -2 plus 4, you will get plus 2. So you just need to put plus 2 over there. Done. Yeah. Now, the MnCl4 2- complex does not contain any 180 degrees bond angle. Yeah. So if you have, okay, 4 bonding pair over there, yeah. So if they ask you to draw a 3-dimensional diagram to show the shape, okay, so quite simple. Just put the Cl over here. Just put the Cl over here. See how it is drawn. Yeah, 2 straight lines. Okay, one is going to be showing directly over here. Okay, so one over here, another one over here. Okay, then another line is going to come over here. Okay, to coming out from this paper. Okay, which is going to be another Cl. Another line is going to be, it's going to go behind the paper. Okay, so I will give you something like this, and that is going to be the Cl. So this is tetrahedral shape. So you need to show, okay, they say state 1 bond angle in your diagram. The angle is 109.5 degrees. Okay, make sure you show the bond angle in your diagram. Okay, so the next question is going to be a solution of cobalt 2 sulfate. Okay, they contain complex ion. Yeah, this is going to be something you need to memorize. Yeah, transition elements. Okay, if you memorize and you go to the exam and this question came out, yeah, this is going to be a jackpot for you. Yeah, but if you don't memorize, yeah, maybe, yeah, it's going to be difficult. Yeah, nothing to say. So a solution containing, okay, this cobalt, okay, ion, okay, they are reacted separately with all this. Okay, so since in 2021, okay, they have asked about cobalt, maybe, yeah, the future, those who are sitting for the paper 4, maybe you can prepare for copper. Yeah, so in our syllabus we have cobalt and copper, so maybe you can prepare for copper. Yeah, no need to prepare again for cobalt. Yeah, now they ask you to write the equation for each of the reaction and state one observation that can be made. So if you have, okay, if you are reacting with OH minus, okay, the equation is going to be, okay, I think no need to rewrite again. Okay, I can actually make it big again. Okay, this one I have already done earlier. Okay, so if you write it big, okay, you are going to get, okay, this formula CO, okay, the 2H2O is removed. Okay, the OH, 2 of it will do the ligand exchange. Okay, and you will get this. Okay, and this is going to form, okay, a blue precipitate. So this is solid. Okay, so this is going to be aqueous. Okay, this is aqueous. Okay, this is liquid. So you are going to get a blue precipitate. Okay, it's formed. So in your exam, don't write PPT. Yeah, write down precipitate. Okay. Now the next, okay, is going to be when you react with ammonia. Okay, same, I have done it earlier. Okay, so I will just enlarge this. Okay, refer to my lecture notes or your submissions. Okay, we have done all this, okay, last time. Okay, when you react, okay, with ammonia, all, okay, the water molecules are exchanged with ammonia, and when it is exchanged, you are going to get a straw solution. Yeah, so a straw solution is formed. Okay, so I'll just bring it over here. Okay, straw solution form, so you can just put aqueous. Okay, this is liquid. Okay, this is going to be aqueous, and this is going to be aqueous. Okay, so you just need to know what is the observation. Yeah, next is going to be if you are reacting with Cl minus. Yeah, what will you get? Okay, so you are going to get, okay, this COCl4. Now COCl4 is also going to be a blue solution. Yeah, so I'll just put it here. Okay, you are going to get, okay, this blue solution, which is going to be this is a tetrahedral also. Yeah, so it's going to be aqueous. This is liquid. Okay, this is aqueous, and this is going to be aqueous. So blue solution is going to be formed. Yeah. Now the next part, okay, the easy part, name the type of reaction occurs in B3. Yeah, not only in B3. Yeah, in all B1, B2, B3. Yeah, so they are going to replace the ligand. So this is going to be known as ligand exchange. Okay, so this is going to be a ligand exchange reaction. Now, cobalt, okay, forms the complex ion. Okay, so you have this 2 ammonia and En. Yeah, En is a bidentate ligand. So if you have a bidentate ligand, it means one En has 2 coordinate bonds. Yeah, so if you have 2 bidentate, then 4 plus another 2, 6. So we are talking about 6 coordinate bonds. Okay, so the abbreviation En is used for the bidentate ligand. So they have given you information over there. The complex ion shows both geometrical and optical isomerism. Yeah, define the term bidentate ligand. So what is bidentate ligand? Is a species, okay, that can donate 2 lone pair, okay, to form 2 dative bond to the transition metal or metal ion. Okay, so I prepared earlier also, so I'll just, okay, put it over there. Okay, so it's going to be a species that donates 2 lone pair, okay, of electrons, okay, to form, okay, okay, 2 dative bond, okay, to a transition metal or metal ion. Okay, now draw three-dimensional diagrams, okay, for the two optical isomers of this. Yeah, so do remember they say that they can show both geometrical and optical isomerism. Okay, so and I told you they have 6 coordination number. So if you have anything that has 6 coordination number, they will look like octahedral shape. So if I just put in terms of like this, okay, if I want to draw normally octahedral shape, I will draw something like this. Okay, so I have the ammonia. Okay, 2 ammonia. Let's say I want to show in form of trans. Okay, ammonia over here. Okay, and then ammonia over here. Okay, NH3. So this is a trans. So the trans, okay, we know that if you want to show, okay, in terms of you want to show in terms of 3D, you show them like this, and then the one that is going behind, you show them like this. Okay, like what we did earlier. Yeah, and then okay, this one similar, they will go here, and then this one. So we have En. Okay, we have En, but they ask you to show in this form. Okay, what you can do is, okay, we know that we have one up, and we know that we have another line down. Okay, 6 coordination number. Okay, you can actually draw, okay, something like this connected to this, okay, and this connected to this. So I can just draw N over here, and I draw N over here. Okay, then I have this and this put like this. Okay, just follow. Okay, and then the same thing. Okay, I have N over here, I have N over here. You put like this, you put like this, and you draw like this. Okay, this is going to be a molecule. Yeah, this is one of the way to draw. Yeah, one of the way to draw, and this is going to be a trans isomer. Yeah. And do remember, if you want to draw, okay, in terms of cis, I have drawn beside. So maybe you can have a look, okay. So if you draw cis, okay, then it's going to be, what is the difference of cis? Cis is going to be the ammonia is going to be side by side. So side by side. So this is also acceptable, okay. But since we are talking about, okay, the cobalt is there. So since we are talking about optical isomerism, okay, if you have drawn like this, then you have to draw the corresponding version, the optical isomer for this. So I will draw something like this. Okay, so same. Okay, this one going behind. Okay, this one going behind, coming out. So you have, okay, you just need to show a mirror image. Okay, so this one is nitrogen. Okay, up, down. Okay, we know this is nitrogen. Okay, and then ammonia. So this one must be ammonia. Okay, and this must be ammonia as well, NH3. And this must be the nitrogen. Okay, so the nitrogen. So how to do? Put like this, join. Put like this, join. Yeah, so this one is that. Yeah, optical isomerism with case trans. Yeah, if they ask you to draw for cis, then you draw for cis like this. Yeah, and then with the corresponding mirror image. Okay, so make sure, okay, you refer to how I draw over there. Make sure you draw properly. Yeah, next question, number 6. An excess sodium iodide is added to a solution of copper 2 sulfate. Iodine and a white precipitate of copper iodide form. Yeah, so they have given you, okay, they say NAI, okay, they are adding with copper 2 sulfate, so CuSO4. They are giving you, okay, iodine, which is going to be I2. And then they give you a white precipitate of copper 1 iodide, CuI. Okay, so of course, okay, this is not complete, okay, because I need to have Na and SO4, so plus Na2SO4. Okay, so I just need to balance this. Okay, you have 2, so of course I need to put 2 there. And then sulfate is balanced, sodium is balanced, copper is balanced, I is not balanced, okay, but I see here there are 2I. I have 3I. How to make 2I? So I have 1, so I just need to put half over there. Okay, if I have half over there, if I times everything by 2, yeah, I will get the answer. So the 2, you times everything by 2, 4 NaI plus 2 COSO4. You are going to get iodine, 2 CuI plus 2 Na2SO4. You are going to get the reaction, yeah, the equation. So this is going to be, you just need to write down. So it's 1 mark, yeah, it's 1 mark. So they didn't tell, okay, if they didn't tell you about the state, no need to write. But if you want aqueous, okay, this is aqueous, okay, this one, iodine, in this case, is it going to be solid? They didn't mention, yeah, so maybe I'll just put solid over here. A white precipitate, so it's going to be solid. Okay, this one is aqueous. Okay, now explain why copper 2 sulfate solution is colored. Now copper 2, yeah, is actually under transition element. Yeah, so the reason why copper 2 is colored, yeah, because there is going to be d orbital splitting. Yeah, so d orbital splitting, they are going to be split into 2 different energy level. Okay, the electron in the lower energy level, okay, the electron, okay, they will become excited, okay, at the lower energy level, okay, lower energy level, they become excited and promoted, okay, and promoted to higher energy level, by absorbing the wavelength of light. Okay, so once they actually absorb the wavelength, okay, you can see the color. Okay, the color seen is going to be complementary color. Okay, color to the wavelength absorbed is seen. Okay, that's why it's going to be colored. In this case, copper 2 sulfate is blue in color. Yeah. Now, suggest, okay, why the precipitate of copper iodide is going to be white. Okay, why the precipitate is going to be white in color. Okay, the copper 1 iodide. Okay, if you look at copper, okay, copper itself, okay, is going to be 4s1 3d10. Okay, so this is going to be the structure of copper. So if it is going to be copper 1, okay, that's going to be Cu plus. Okay, 1 electron is gone. So if it is 1 electron gone, is copper plus is going to be 4s0 3d10. So you can see that the d orbitals are going to be completely full. Okay, the d orbitals, okay, are, okay, the d orbitals are full. So if the d orbitals are full, even though when the splitting, the d orbital splitting happens, okay, the electron from lower energy level cannot be excited and promoted to higher energy level because the d orbitals are full. Okay, so they are not going to give you any complementary color. Yeah, so that's the reason why copper 1 iodide is white in color. Yeah, now use the suitable E values, okay, from the data booklet, okay, to predict whether iodide ions can reduce, okay, Cu2 plus to Cu plus. So this one, okay, you need to look at the data booklet. So the data booklet will always give you the value, okay, in terms of, okay, reduction. So I have taken the value and I will put it over here. Okay, the value, okay, you can see the value, okay, is going to be, I have rearranged the value. Okay, you see 0.54 and 0.15. Okay, why I rearrange the value? Because I want the value, okay, so that this is going to be 0. Okay, higher up is a bigger positive value. okay, and lower down is going to be negative value or smaller value. So if you look over here, if you rearrange, maybe 0 is somewhere here. This is 0.15, 0.54, slightly higher. Yeah. Now, when you arrange this, okay, if you look at it, okay, I taught you about this SOA and SRA. SOA is strong oxidizing agent. Top left corner, yeah, is going to be strong oxidizing agent. On the bottom right is going to be strong reducing agent. Okay, if you look at it. So now, okay, you want to find out whether I minus, okay, is able to reduce copper to plus. You see, I minus is not a strong reducing agent. Okay, because I know copper plus, okay, is a stronger reducing agent than I minus. Okay, they are the one that is going to be able to reduce I2. Okay, so here predict whether either ions can reduce, okay, Cu2 plus to Cu plus. The answer is no. Okay, why? Okay, because Cu plus, okay, is a stronger reducing agent than, okay, stronger reducing agent than I minus. Therefore, okay, therefore I2, okay, is the one, okay, the one reduced instead of Cu2 plus. Okay, this is how you answer. Okay, but of course, okay, you need to give the values. Okay, make sure when you explain this, you write down the values, you arrange, yeah, you write down properly. Okay, then you tell, yeah, why. Okay, because it has this value and so on. Okay, but this one must be there. Okay, now the next question is, okay, excess sodium iodide is added, okay, and then copper 1 iodide forms as a precipitate. After the precipitate, okay, Cu plus is much lower than 1. Okay, so use this information, okay, and your answer in C to explain how relevant electrode potentials change and why I minus ion can reduce copper 2 plus ion. So here, okay, when you look at it, okay, when all these are happening at 1 mole per dm cube. So after the precipitation, if the copper plus is much lower than 1, okay, so if I take this thing and I will, if I bring this down, okay, if I copy and bring it down here, okay, I can say that, okay, so this one is SRA, SOA. Now, I can say that, okay, if this one, okay, copper plus is going to be lower than 1 mole, okay, so if it is lower than 1 mole, what will happen, okay, you just use the LCP principle, Le Chatelier's principle, okay, where, okay, the position of the equilibrium is going to be shifted to the right. Okay, when that happens, okay, this number is no longer going to be 0.15. Okay, it's going to be greater than 0.15. So if they are telling, okay, if greater than 1.5, okay, then we need to tell why it can reduce copper 2 plus. Okay, so if it can reduce copper 2 plus, it means that, okay, it means that this value, okay, has exceeded 0.54. Okay, it means this value may be 0.6, for example. Okay, it became 0.6. What will happen now? Okay, maybe copper 2 plus electron to give you copper plus, maybe 0.6 now. And then I2 plus 2 electron, 2I minus 0.54. Okay, and we can actually just use, okay, when I arrange this, so this is SOA, this is going to be SRA, strong reducing agent. So I know that I minus is a stronger reducing agent compared to Cu plus. So of course they can reduce the copper 2 plus now. Yeah. So this is going to be how you apply. So the answer over here, okay, you explain how relevant the electropotential. So you just say the E value, okay, will change from 0.15 to, okay, bigger, okay, than 0.54. Okay, once it becomes bigger, okay, then, okay, I minus is a stronger reducing agent, okay, reducing agent than I minus. So it reduces I2, okay. So it reduces, sorry, it will reduce Cu2 plus. Cu2 plus to become Cu. Okay, so you refer to here. So you explain based on that, yeah. So next, okay. So all the reactions the same if copper is copper instead, yeah. This one, okay, Donna, I think please refer to the marking key, okay, that not marking key, the submission. Yeah, you can check in the Google Drive. Last time you submitted worksheet for me on the reactions involving transition elements. Okay, remember the chemistry assignment. Yeah, so refer that. Okay, so it's not the same. Yeah. So next, okay, is going to be question number 7. Yeah. So now, okay, 1 hour 30 minutes. Okay. So now, okay, let's continue. Question number 7. The structure of phenylethanoic acid. Okay, they have given the structure phenylethanoic acid. This one is shown. Okay, give the number of different peaks in carbon 13. So now we are going to talk about carbon 13 NMR. So how many number of peaks? Yeah, so I have done is 6. So I'll show you why it's 6. So this is going to be one environment. Okay, so 1. Okay, so number 1. This is going to be another environment which is attached to 2 hydrogen, and left is this COOH, and right is going left is going to be the phenyl group, okay, and so on. So you have 2. This one is going to be 3, okay. And last time I told you, whenever you are dealing with this, okay, involving benzene and so on, okay, just put like this, okay, so that it's symmetrical. Yeah. So if this one is 3, automatically this is going to be another environment, number 4. Okay. But now, okay, since this one is going to be overlapped directly, okay, you can fold them. Yeah. So it's going to be, this is 5. Okay, the same. This one and this one, they are the same. And this is going to be a different environment, 6, but they are the same. Yeah, with this 6. So there are total 6, okay, environment. Okay, so 6 number of peaks. Okay, I've written over there. And then they say phenylethanoic acid. So this is the one in the diagram is phenylethanoic acid. Ethanol and phenol can all behave as acid. So now we compare and explain the relative acidity of these 3 compounds. So you should know, yeah, the one that is going to be most acidic, okay, normally in your syllabus, we learn carboxylic acid. So this one, okay, the phenylethanoic acid is going to be similar to carboxylic acid. So they are, okay, they are going to be a stronger acid. Why? Because the presence of the O, yeah, so the bond, okay, this O, okay, they are going to withdraw the electron, okay, and then they are going to have this negative inductive effect where, okay, the bond, okay, they are going to form a stable ion, okay, an ion over there. So the bond between O and H is bigger, so H plus is easily given out. Okay, so in this case, okay, the most acidic is going to be phenylethanoic acid, okay, phenylethanoic acid, followed by, okay, you compare, okay, phenol, okay, and ethanol, okay. Please always remember, phenol is always a greater acid, okay, than ethanol. Okay, why ethanol? Okay, C2H5OH. Okay, you have electron donating group. Okay, if you have electron donating group, okay, they are going to donate the electron. Okay, so when they donate the electron, they are going to reduce, okay, the negative ion over here. Okay, when they reduce the negative ion over there, what will happen? The ethanoic ion, okay, so you have this and this. If this is going to be reduced, the negative charge is going to be it will give the electron, so the electron is going to be more negative. Okay, so when you have more negative, okay, this and this, they can join. Yeah, they can join, and they have tendency to go and form the C2H5OH. So in that sense, okay, the H plus is not being formed. Yeah. So for phenol, okay, for phenol, it's going to be the benzene ring. So you have OH. Okay. The lone pair of electrons, okay, for the OH, they go and overlap slightly with the benzene ring, so they become delocalized. So in that sense, they have tendency to form phenoxide ion, which is going to be stable, yeah, and they will give you a lot of H plus. So that's the reason, yeah, why, okay, phenol is more acidic. So if they ask you to compare and explain, yeah, when you explain, okay, you need to explain like what I explained just now, okay, the C double bond O, O, H, okay, so the electron, okay, O is electronegative, is a negative inductive effect. They are going to take the electron, okay, and form, okay, the delocalization, okay, along the oxygen, carbon, and O. So that is going to weaken the bond between O and H. Okay, so that is the first explanation. So the H plus is going to be able to be given easily. The phenol, okay, I have explained just now, okay, you just need to explain that, okay, the lone pair of electron, okay, they become delocalized, okay, into the benzene ring by overlapping with the pi bonding system. So they are going to form a stable ion, okay, phenoxide ion, and the H plus, they give you more H plus. For ethanol, okay, when you have, okay, electron donating group, okay, attached to the ethanol, so the C2H5O minus, which is the ethoxide ion, okay, the negative charge is going to be more. So if the negative charge is more, the H plus and the negative charge, they are going to actually join together, okay, to form more C2H5OH. The position is shifted to the left, okay. So it means that the H plus is less formed. Okay, so if it is less formed, okay, therefore you don't have a lot of acidic condition. So that is going to be what you need to explain to in order to get the 4 marks. Yeah. So C, okay, phenylethanoic acid can be synthesized, okay, using benzene as a starting material. Okay, in the first stage of this synthesis, okay, benzene, they react with chloromethane in the presence of AlCl3 catalyst to form methyl benzene. So they say that, okay, it forms 2 ions, okay, and one of these is going to be a carbocation. So write an equation for the reaction between chloromethane and AlCl3. So you just need to write AlCl3, okay, you react with CH3Cl, you are going to get AlCl4 minus plus CH3 plus. Okay, this is going to be, you are creating, because this one, okay, is going to be electrophilic substitution reaction. So it means that you are going to create electrophile. Okay, so the electrophile, this is the electrophile. Okay, so CH3 is going to be the electrophile. So this electrophile, they are going to be attracted to the rich electron density, in the pi bond. Yeah. So the one that if you have the circle over there, okay, the benzene ring, yeah, the benzene ring is going to be rich in electron. So the electron, so when you show the curly arrow diagram, yeah, the curly arrow diagram is going to show the movement of electrons. So you need to show, okay, you need to show okay, that the electron, since the product is over here, so I am going to show from here, it's going to go there. Okay, so it must be curly. So I'll try to draw like this. Yeah, curly, it goes there. Okay, so what will happen? Okay, the intermediate that we are going to have, okay, when the electron goes there, okay, what happens is going to be, you are going to have, okay, the circle is going to be broken. So you have something like this. This is positive. So you are going to have, okay, one H over there, another one is CH3. So this is intermediate, okay, and it's not stable. So it will become stable, okay, when you bring the electron from here, it will come over here. Okay, the two electrons will start to come in. Okay, when they come in, then they form bonds. Okay, so the H plus is given out. Okay, so if you want, you can just write down over there the H plus is given out. Okay, so this is going to be the intermediate and so on. So you need to write down like that. Yeah. Now, so a three-step synthesis, okay, of phenylethynoic acid from methyl benzene is shown. So now, okay, this one is going to be, you have the methyl benzene. So of course, this one is CH3. Okay, so if I have methyl benzene, okay, and I'm going to, you see the carbon, this is carbon. So it means that one of the H, okay, so if you have CH3, it means one of the H is going to be replaced by Br. So the only way where you have the H being substituted by Br, okay, that step number one is going to be, you need to use the UV light. This is going to be free radical substitution, okay, and okay, Br2, okay, the regions is going to be Br2, okay, and then you use the UV light, okay, and then you will get the free radical substitution, okay, that you have over there, okay. Then, okay, we need to use form a compound Q, okay, but before I look at compound Q, I just have to look over here, C, and then this C, and then this carbon is here. But suddenly I have another C, okay? So if you have additional carbon, okay, in your organic compound synthesis, okay, you must add carbon in form of what? There is only one way to get that, which is going to be, you need to react with KCN. Okay, this KCN must be ethanolic and it must be heated. So that's why, okay, step number 2, you must react with KCN, ethanolic, okay, and then you must provide heat. Okay, what will happen if you want to suggest the compound Q? Okay, so if I delete this, okay, if I want to suggest, okay, this compound will look like this. Okay, so I'll draw, okay, this one, okay, so you have C, another C, okay, and then I have another CN over there, okay. So this is going to be one carbon, another carbon, okay. So let me draw properly. Okay. So you have CN over there. So this is a nitrile, okay, nitrile. Step number 3, okay, how do you change nitrile, okay, to carboxylic acid? So in this case, you need to use dilute, yeah, dilute ACl, okay, and you need to heat them, okay. You can actually change, okay, the nitrile, okay, into carboxylic acid. So, okay, dilute ACl, and then you heat, okay, so you will get that compound, okay. So this is very, very important, okay. Now draw the structure of organic byproduct, okay, that forms in step number 1. Okay, step number 1, okay, you see is going to be still free radical substitution. Okay, if you say organic byproduct, it means that, okay, do remember free radical substitution, they can continue to react. So most probably they say one byproduct. So let's actually draw one byproduct. Maybe, okay, I will draw, okay, a benzene structure. Okay, then I put Br, okay, one Br over there. Okay, then this Br and this Br. So it means I can substitute all, okay, with Br until everything is completed, right, to change. So this one can be one Br, one organic byproduct. Okay, you can actually draw another with two Br also. Okay, so depends on you, but I will leave it like this. Okay, this is going to be one organic byproduct. Okay, now next, okay, number 8, phenylamine. okay, is and then ethyl amine can be distinguished, okay, by adding aqueous bromine. Yeah. So if you use phenylamine and ethylamine, okay, this is amine. Okay, phenylamine is special, okay, because phenylamine is the one that will react with aqueous bromine. Amine, they do not react with aqueous bromine. So state what is seen when aqueous bromine is added to phenylamine. Okay, two observation can be seen. Okay, the bromine water is brown. Okay, so the brown water is going to become colorless. Okay, so that is one. And then, okay, they are going to form phenylamine. Okay, if you have phenylamine, they are going to form this NH2. They will react and give you Br over here, Br over here, and Br over here. This is a white solid. Okay, so white solid is formed. Okay, white solid is formed. Suggest, okay, what is seen when aqueous bromine is added to ethylamine. Ethylamine, so the brown water remains. Okay, the brown solution remains or no change. Okay, remains or no change. And then draw the structure of organic product formed when excess aqueous bromine is added to phenylamine. So I told you, phenylamine is going to be 2,4,6 directing. Yeah. So if you are using excess, so all the 2,4,6 is going to be used up. So I will just bring it over here. So this is what that is going to be formed. So name the product that you have drawn over here. So this is 2,4,6, 2,4,6. Okay, tribromo, okay, phenylamine. Okay, and that is going to be the answer. Yeah, the product. So let's move on. Question number 9. Okay, compound T is made of 3-stage synthesis. Okay, in stage number 1, phenylethynoic acid, okay, reacts with a suitable reagent to form compound R. So if I look at this, okay, it's going to be carboxylic acid. Then you have the acyl chloride. How do you change carboxylic acid to acyl chloride? Okay, you can actually react with PCl5, PCl3, SOCl2, up to you. Okay, so maybe I will react with PCl5. Okay, and then the condition they didn't ask, but do remember, if you are using PCl5, then you need to use room temperature. If you are using PCl3, then you use heat. If you use SOCl2, then it's room temperature. Yeah, but two types of gas will be released, HCl and SO2. Okay, normally we don't like to use this because both of these gas are poisonous. But the good thing about this is going to be you do not need, both of them are gas. So the product, okay, you do not need to purify the product. It's already there. Yeah, you don't need to separate and so on. So it's already there. So it's good. Okay, but PCl5 is more popular, yeah, because okay, it happens at room temperature, okay, and also gives you HCl. Okay, so this is more common, yeah. PCl5 is more common, okay, and because they give you less poisonous gases, yeah. So PCl5 is selected. Now in stage 2, yeah, compound R reacts with ethyl amine to form compound S. Okay, so this one, acyl chloride with amine, they give you this compound. Now, name the functional group formed in stage 2. Yeah, the functional group, you see this group. Okay, this is going to be amide group. Okay, this is amide group. Okay, and identify the other product formed in stage 2. So you see NH2. So if I have NH2, what happens? Okay, C2H5. So this H will join with the Cl. So we are talking about the HCl. So identify, don't just write HCl. Identify means you need to give name, hydrogen chloride gas. Okay, if they ask you what is going to be observation, yeah, hydrogen chloride gas is going to be white fumes. Yeah, so if they ask you what is the observation, white fume, but hydrogen chloride gas. Yeah, this is not going to be hydrochloric acid. Please take note. Yeah. Now, the next, okay, is going to be in stage 3. Compound S reacts with a suitable reagent to form compound T. Yeah. So what is the difference over here is you have the amide. Okay, amide is changing into no double bond O, so it's going to change into amine. Now, how do you change amide to amine? Yeah, so you must actually do reduction. Okay, the reduction of amide can only happen with LiAlH4. Okay, in dry ether. Okay, dry ether. So this one must be done. Yeah, so this one, state the formula of the suitable region. So LiAlH4 in dry ether, but no need to of a suitable region. So it's okay, just write info. Okay, and then do remember, this reaction, the reducing, whenever we are talking about reducing, since we are changing amide to amine, is reduction also. Okay, but if you have nitrile, whenever you react with KCN, ethanolic, and so on, you have nitrile. This nitrile, you can change the nitrile into amine. Okay, and you can use two types of reducing agent. One of the reagent is the one that we discussed, LiAlH4 in dry ether. Okay, another one that you can use is going to be hydrogen gas in nickel catalyst and nickel catalyst. Yeah, you can actually do that. That is given if it is nitrile to amine. Yeah, so now we are talking about amide to become amine. Yeah, so name the type of reaction that occurs. Yeah, we already discussed about this. This is going to be a reduction reaction. Okay, let's move on. The relative abundance of molecular ion peak in the mass spectrum is going to be 62. Now, you want to actually calculate the relative abundance of M plus 1. Okay, so M plus 1, this one we have learned, to calculate, the number of carbon, in the compound. So if you have ethyl amine, this is ethyl amine. Yeah, this is ethyl amine. And we know the number of carbon is 2. Yeah. So the formula is, in order to calculate the number of carbon, is going to be 2 equals to, number of carbon is already, we know, is 2. Yeah. 2 equals to, and then 100 divided by 1.1, times the abundance, abundance for M plus 1. This is what we want. And then divide by abundance of M. But the abundance of M is 62. So 62, I just put it in. And you just need to calculate that. So calculate, this abundance. So you will get 2 times 1.1 divided by 100, equals, then times with 62 equals to abundance. So the abundance, if you calculate, you will get 1.36. 1.36 is the relative abundance. You can calculate yourself. Now, the mass spectrum of compound T contains several fragments, and then the M over E values of two of those fragments is 29 and 91. Do remember, this is still, the old syllabus, where they are still testing you more on the mass spectrometer, but I told you, the mass spectrometer is already in AS now. I doubt that they will ask you this many, but it's no problem, because I think 1 and 2 is still 3 marks. They can still ask like that, so still no problem. Now, if you have the fragment 29 and 91, I have taken the T from here. I have copied and put it over here. So if you want the M over E 29 and 91, the best way to look at it is going to be, you just need to put the CH3, you put like this, and then we calculate one by one. Like for example, if I have CH3, then 12 plus 3, so 15. CH2 is going to be 12 plus 2 is going to be 14. NH, 7 plus 1, so it's 8. Then you have CH2, and then CH2. CH2 is 14, 14, so that is going to be 28. So this one, for this one is going to be C6, H5. C6H5. So C6H5 is going to be 12 times 6 plus 5. So that's going to be 72 plus 5. That's going to be 77. So if they want 29, so see which combination gives you 29. And I can see 14 plus 15 is 29. So I know it's going to be CH2, CH3, and then put plus. Okay, that is going to be the structure of the ion. If I have 91, okay, 91 most likely the bigger number, so 77. 77, I try first, okay, there's 14 and 14, so let's 14 first, okay. So 1, okay, then I have 8 and 9, 91. So it means that the 14 up to here, okay. So it means I'm talking about, okay, C6H5, okay. Then there is CH3, sorry, CH2. Then plus, okay, so 14. Okay, 14 plus 77, so I'll get 91. So that is going to be the part that they want. Okay, now the next question is the proton NMR spectrum of compound T. Okay, it shows the hydrogen atoms in different environments. Okay, 6 of the environments are shown in the structures by using the letters. Yeah, they have given letter A, B, C, D, E, and F. Yeah, so use this letter to answer the following questions. Okay, so here, okay, proton D, okay, they say that does not cause splitting for proton C, okay, and E under the condition used. Yeah, so each answer may be one, more than one of the letter. Yeah, so here, okay, identify the proton with a chemical shift 6 to 9. This one, if you go and look at the data booklet, okay, you will see that, okay, any proton that is attached to benzene ring. So I already checked for you. Yeah. So any proton that is attached to benzene ring, so you can see the proton that is going to be attached to the benzene ring. This is the proton, okay, attached to the benzene ring. Yeah, so it means we are talking about A. So I put A. Identify the proton whose peak will disappear when D2O is added. Okay, the rapid exchange, okay, will happen whenever you have the proton attached to nitrogen or the proton attached to O. Yeah, so the one that will disappear is going to be for D. Yeah, so D and H. Okay, next, identify the proton whose peak is going to be triplet. Okay, triplet means, okay, the neighbor must have 2 hydrogen. So if I look at F, okay, the neighbor has 2 hydrogen. Okay, so E possible. Okay, let me erase everything. E is possible. Okay, if I look at D, okay, the neighbor, okay, in this case, there's no splitting, yeah, so no need to worry about D. Okay, let's actually talk about F. Yeah, for F, okay, the neighbor has 2 also. Okay, so neighbor have 2, so E for F, yes. For E, they are going to be 3 hydrogen. Okay, therefore 4, so not E. Okay, cannot be E. Sorry. So it's supposed to be for F. Okay, for F, 2 hydrogen here. Okay, 3 triplet. So this one, okay, has 2. Okay, this one, if I compare, okay, it has 2, so it will have triplet. Okay, for B, it has 2. Okay, therefore this one also triplet. Okay, if you look at the A, okay, A is going to be 1 only here, so double only. So therefore, okay, you will have B, C, and F. Okay, so you can have 3 B, C, F. Identify, okay, the proton, okay, or the protons with the lowest chemical shift. Okay, if you look at the data booklet, the lowest chemical shift is the one that is alkane. Okay, so the one that is alkane that is attached to carbon only, yeah, nothing to benzene or nitrogen and so on. So the one that will be the lowest, okay, the simple one is going to be the F. Okay, the F is going to be attached to another carbon over there, so the hydrogen is attached to carbon only, so this is going to be the lowest. Okay, so it's going to be F. Okay, now next, number 10. So valine, okay, if you look at your data booklet, okay, the R group for valine is going to be this, so I'll keep it over here. And then lysine, okay, the R group for lysine is this. So they say that, okay, they are both amino acid. The structure of this amino acid can be found in the data booklet. So the isoelectric point of amino acid is a pH, okay, where they exist as zwitterion, yeah, zwitterion, yeah. The isoelectric point of valine is going to be 6, okay, and then the isoelectric point of lysine is 9.7. So at this point, they are going to exist as zwitterion. So draw the structure of valine, okay, at 6. So it means the one where they are going to exist as zwitterion. So valine, carbon, okay, they must have COOH, okay, they must have NH2, they must have hydrogen, but the R, okay, we know the R is going to be given CH, okay, CH, and then they have CH3, CH3, okay, so we can draw that, okay, so this one, I bring it here. Okay, so I have this as my valine over here. So here, okay, do remember this is not 100% correct because you need to mention about being zwitterion. So this one minus, okay, and this is going to be the 3. And then you will have plus. Okay, this is going to be the structure of valine at pH 6. So let's actually look at a solution of lysine. Yeah, the solution of lysine is produced with pH 9.7. Yeah, so it's still isoelectric point. Okay, so the dilute sulfuric acid is added slowly. Okay, until the pH is going to be 1. So from 9.7, okay, which is going to be having the zwitterion, they are going to be added until, okay, they are going to be pH 1, until they become acidic. Yeah. The sulfuric acid reacts with lysine to produce different organic ions that are not present in significant concentration at pH 9.7. So at pH 9.7, there's something, but now, okay, they are going to have different. Draw the structures of 3 organic ions, okay, so they want ions, okay, that form during the addition of sulfuric acid in the boxes. Okay, draw the organic ion present at pH 1 in box C. Okay, so it means if it is lysine, okay, just lysine alone, lysine is going to be all this here. So you know that, okay, if you have this base, okay, it's a zwitterion at 9.7. Okay, the zwitterion, okay, is going to be you are going to have a basic amino acid, so they are going to react. Okay, react with acid. So at pH 1, okay, what do you expect? Okay, the pH 1, okay, you are going to have, okay, this part, the R part is also reacting. Okay, so what will happen over here is, okay, we know that, okay, I put over there, if the compound, okay, they have the COOH group, okay, they have the COO minus, okay, earlier, okay, and then they have NH3 plus the zwitterion, yeah, so at 9.7. And then this part, the NH2, okay, they are going to exist over there, NH2. So when you react, okay, when you react, so what happens over here is, okay, because pH 1, okay, the H plus, okay, they are going to react, okay, they are going to come and join with the COO minus to give you COOH, okay. So NH3 plus, they will stay, yeah. But do remember, okay, the NH2, okay, is going to be basic, okay. So basic will also react with the H plus, okay. So when they react with the H plus, they are going to get NH3 plus. So what will happen, okay, if I draw, okay, let me draw like this, okay. So C, okay, you have H, and then the R group is going to be CH2, okay. So maybe I'll just put CH2. How many? 1, 2, 3, 4. 4, and then NH2. So you have COO minus, and then you have NH3 plus. Okay, this is going to be, if it is exactly as a zwitterion. Yeah, so I'll just put it here, exactly zwitterion, and I can copy this. I'll copy to all first. Okay. Now, what happens over here if you have pH 1? Okay, if you have pH 1, so you are going to have, okay, this COO minus, okay, the H plus, they will come over here. So I will erase this part. Okay, so you are going to get COOH. Okay, this one, okay, still stay. And then this is basic. Okay, so H plus, when H plus comes, yeah, they are going to receive, receive the H plus, okay, and they are going to give you NH3 plus. So you have this compound, okay, for pH 1. Now let's actually look at the other two. Yeah, while from 9.7, okay, moving to become 1. Yeah, so one of it, okay, is going to be, you see, like normal. Yeah, so the first part is going to be as the H plus is increasing. Yeah, so the H plus is going to react with the COO minus. So what you will have, okay, you can just put, okay, this one is going to come over here. Okay, so maybe, okay, the NH2 still, okay, still not in excess to pH 1, so still maintain like this. Okay, don't react first, still okay. Yeah, for A, okay, another compound. Okay, what happened? Okay, so apart from coming towards COO minus, okay, the H plus can go to the NH2. Yeah, so just now H went here. So now instead of going to there, so it will come over here. So they are going to give you, okay, NH3 and then plus. Okay, so that's why, okay, you have NH3 plus. Okay, so there are 3 possibilities. Okay, the H goes to the NH2, the H goes to COO minus, and then the H goes for both. Okay, at pH 1. Okay, these are the 3 things. Okay, so to make it very clear, okay, I'll just erase this part so it's better now. Okay, draw the structure of dipeptide, valine and lysine. Yeah, so valine and lysine, okay, just now, okay, I think let's actually take this. Copy, paste. Okay, this is lysine. Okay, lysine, but I need to edit a bit. Okay, so this one is NH2. So NH2, COOH, and H2. Okay, now, so this one is going to react. Okay, it's going to react with valine. Okay, valine is this one. Okay, so I just copy it here. Okay. So I edit a bit. Okay, so this one COOH and H2, and then this one CH3. So maybe I'll just put CH3, CH3. Okay. Now, so they want a dipeptide. Okay, a dipeptide. The peptide bond should be fully shown. Okay, think if you want to do that, okay, easier if you do like this, COOOH. Okay, and then this one, okay, you put the hydrogen like this. Okay, easier to show. So now, okay, the OH from here and the hydrogen over here. So you take out, so you will have NH2, CH, CH3, CH3, H, and then C double bond O, N, H down, CH, CH2, 4, NH2, and then COOH. Okay, so this is a dipeptide. Okay, and they ask you, okay, it should be fully displayed. Okay, if you want, okay, if you want, you can indicate. Okay, this is the peptide linkage or peptide bond. Okay, done. Okay, now Yeah, that's it. Okay, that's it. Okay, so all done. Okay, done in 2 hours 10 minutes. Okay, so any comments? Okay, so you have comments, you type the comments over there. If you have any questions, so I'll just wait for you guys to ask questions. So who are the 6 people still here? Okay. Any questions? If you have any questions, you can ask me now. Okay, then I'll try to answer. Okay, if there is no question, if you have done, okay, it's good. Okay, we have done. Okay, if you have further questions, okay, you can actually ask me later. Okay, so for now, okay, that's it. Okay, so let's actually review what we have seen. Yeah, question number 1. Okay, they talk about electrochemistry, yeah, quantity of charge, and so on. Okay, and after that, okay, gives free energy. Okay, number 2, okay, pKa, and so on, buffer solution. Okay, and then number 3, okay, electron affinity. I think this is a very interesting question, yeah, when it comes to Born-Haber cycle. And we saw question number 4. Okay, I think they talk about the solubility. I think very interesting because they try to relate to the lattice energy and so on. Okay, and let's see. Okay, could you go through 7? Yeah, part D. Okay, let's see. 7 part D. 7 part D. This one? Why so difficult? 7 part D. I'll just go through again. Yeah. So 7. Let me see. I'm in the right question. 7 part D. Yeah. For 7 part D, you see it's a 3-step synthesis of phenylethynoic acid. Yeah. So if you want to change, okay, the methyl benzene, okay, into something that has bromine over there, there's only one way. Yeah. You must actually, you want to have bromine over there, you must actually use the free radical substitution. Yeah. So you must use the UV light and bromine. Yeah. So after that, okay, I think the confusion might come, okay, because how come, okay, how do you get compound Q? Yeah, because you need to look at this compound. So if you look at this is 1 carbon, another carbon. Yeah, so 1 carbon, another carbon. So you have 2 carbons side by side over there. Yeah. So of course we are not considering all this carbon now. So you can see the number of carbon. Suddenly, okay, the number of carbon is going to be increased over here. There is 1 extra carbon over there. The moment there is 1 extra carbon, yeah, you need to change or get that extra carbon by reacting them with KCl. That's why I react with KCl. You must react with KCl and ethanolic, and then it must be heated. Okay, once you do that, okay, what will happen? The C and C, then you have additional carbon over there. So nitrile group is formed. Okay, so this nitrile group, okay, that's compound Q. Okay, so you need to do something in order to change the nitrile into carboxylic acid. So nitrile, you want to change into carboxylic acid, you must react with dilute HCl and heated. Okay, that's why I put dilute and heated. So you will get this acid. And then draw the structure of organic byproduct. If you don't understand this, it's basically quite simple. You see, when you have the Br, okay, one of the H is substituted by Br. It means that there are, if you have more substitution, yeah, so the remaining H will be substituted, the Br and Br. So I just selected one with the 3 Br substituted. Okay, so that is what I put over there, the 3 Br substituted. Is that okay, Ashley? And then Fredo, is for the colored compounds, do we have to write about the orbitals? The answer is yes, Fredo. But okay, make sure when you're writing about color compounds, make sure, I think generally all color compounds, okay, in our syllabus is going to be based on, you're talking about, make sure when you're writing about orbitals, you must talk about transition metals. Okay, so don't go and actually talk about d orbitals, okay, when you're talking about iodine, why iodine is actually purple in color, don't do that. Okay, you if you're talking about d orbitals, okay, then you need to talk about, okay, you need make sure that you're talking about transition metals, yeah, copper, cobalt, or something like this. Yeah, so do we have to write about the orbitals? Yeah, Fredo, the answer is yes. So someone is keep on vomiting, I don't know, yeah. Shouldn't be watching this. So who else? Yeah, any other questions that you want to clarify? Okay, Ashley. Okay, when maybe I will edit this, okay, the written version, okay, I can actually share through Google Drive later when I put the stream in the video, okay, maybe I'll edit over there, okay, then you can also see, okay, but this one is complete already. Okay, that's all from me today. Okay, have a rest. Okay, see you. Bye. Take care.